This is an overview and implementation in Excel of one of the most important results in number theory and cryptography, the prime number theorem. At the most basic level, the prime number theorem is just a mathematical formalization of a pretty intuitive notion, the notion that prime numbers occur less and less frequently as they get larger and larger. This makes intuitive sense if you consider that in the range from 1 to 100, 25 prime numbers occur, as seen on the left and highlighted in green. But in the range from 901 to 1000, as seen in the middle, only 14 prime numbers occur, and in the range from 9901 to 10,000, as seen on the far right, a mere 9 prime numbers occur. Even though the length of the ranges that we're considering stay the same, the number of prime numbers occurring in each range is decreasing as we consider larger and larger numbers. Important to this discussion is the pi function, denoted pi of some variable n, which is a prime counting function. The pi function is similar to the phi function, the latter of which I discuss quite a bit on this channel, in that it's a counting function. However, unlike the phi function, which, for any given positive integer k, outputs the number of integers less than or equal to k that do not share any common factors other than 1 with k, the pi function works to count the number of primes less than or equal to n. So returning to our earlier example, the pi of 100 would be 25, since there are 25 prime numbers less than or equal to 100. The prime number theorem states that for any real number x, the pi of x is approximately equal to that real number x divided by the natural log of x. More formally, we can say that the limit as x approaches positive infinity of pi of x divided by the quantity x divided by the natural log of x is equal to 1. This latter result is slightly more difficult to understand, but makes a bit more sense when we consider the numerator and denominator separately. Since x divided by the natural log of x is supposed to approximate the pi of x, we can conclude that the ratio, or pi of x divided by the quantity x divided by the natural log of x, should be nearly equal to 1. Or another way of thinking about this is that since pi of x and the quantity x divided by the natural log of x are nearly equal, the result of their division should be near 1. Now, when we add this limit as x approaches positive infinity in front of this ratio, what we're saying is that as we consider larger and larger real numbers x, the result of this ratio approaches 1. In other words, as we consider larger and larger real numbers, this approximation gets more and more accurate. As a result of this, we can also say that since there are roughly x divided by the natural log of x prime numbers that are less than x, if we pick a random integer p between 1 and x, the probability of p being prime, denoted p of p is prime, is about x divided by the natural log of x divided by x, or 1 over the natural log of x. Now, this phenomenon of the limit as x approaches infinity of pi of x over the quantity x divided by the natural log of x equaling 1 demonstrates something called the asymptotic law of distribution of prime numbers. To illustrate this notion a bit more concretely, I'm going to go ahead and switch over to Excel. I've created a chart here, and in my first column here, I have listed steadily increasing values of real numbers x. In the next column, I've computed the pi of these numbers x. So for example, I have in my first space that the pi of 100 is 25, in my second space that the pi of 10,000 is 1,229, and so on and so forth. In my next column, I've computed the natural log of those values of x, and in my final column, I'm going to compute the pi of x over the quantity x divided by the natural log of x. So remember that pi of x counts the number of prime numbers less than or equal to x, and x divided by the natural log of x is the approximation of pi of x. So if we divide pi of x by x divided by the natural log of x, we should get a value that is somewhat near to 1, because pi of x and x divided by the natural log of x should be fairly similar values. And so I'm going to go ahead and compute pi of x divided by the quantity x divided by the natural log of x for all of my x's. So in my first space, I'll say that this is equal to pi of x divided by the quantity x divided by the natural log of x. And I'm just going to do something similar for all of these values here. So here I have 1,229 divided by 10,000 divided by about 9.2. And you get the idea, so I'll just go ahead and finish that up. And so as you can see that per our idea that the limit as x approaches infinity of pi of x divided by the quantity x divided by the natural log of x is equal to 1, I'm getting steadily decreasing values that are getting closer and closer to 1 as x increases. I'll even go ahead and plot this so that you can see this idea more clearly. So I'm going to select my values of x here, as well as my values here, and I'm going to insert a scatter plot. I'm going to change the scale here to a logarithmic scale, and I'm also going to make the minimum value here equal to 1.00 instead of 1.04. So you can see on the graph that as x increases, our ratio pi of x divided by the natural log of x is steadily approaching 1. This is what is meant by the notion of prime numbers being distributed asymptotically. If the limit as x approaches infinity of some function equals L, then L is an asymptote of that function. Similarly here, the limit as x approaches infinity of our ratio pi of x divided by the quantity x divided by the natural log of x is 1, so we have the asymptote of our ratio function being 1. Transitioning back, I'd finally like to discuss the applicability of the prime number theorem to RSA encryption. The prime number theorem is most important to RSA because it shows that part of the key generation involved in RSA is practical. I'm not speaking about the efficacy of decryption here or anything, merely that it's not going to take a huge amount of impractical time just to generate parameters in RSA, specifically the large prime numbers that must be generated by a key generator. For the 1024-bit prime numbers that are used to generate the 2048-bit semi-prime numbers n in RSA encryption, we can represent the 1024-bit primes as 2 to the 1024 power, which corresponds to 309 digits. Earlier, we said that if we pick a random integer p between 1 and x, the probability of p being prime is about 1 divided by the natural log of x. So we can simply plug in 2 to the 1024 power in for x here and get 1 divided by the natural log of 2 to the 1024 power, which is approximately 1 divided by 710. And so we have a 1 in 710 chance, or a probability of, given 710 random 1024-bit integers p, one of them being prime. If we eliminate even numbers, our probability increases to 1 in 355. And so what all of this is showing is that generating big prime numbers for using in RSA encryption is practical, what with a 1 in 355 probability for 1024-bit prime numbers specifically. And so that's been a brief overview of the prime number theorem. As always, I hope this was helpful. Thank you so much for listening, and stay safe out there.